So in this example, we have the electric circuit shown, and we want to find the equivalent capacitance of these four capacitors. All right. In addition, we want to find the electric potential across each of those four, as well as the charge across each of those four. Okay. They have their respective capacitances shown, as well as the voltage for the battery itself. I like this specific circuit because it has capacitors both in series and in parallel. Right? These two are in parallel with one another, but this equivalent capacitance is in series with this one as well as this one. Okay? So we need to be careful in how we calculate the various potentials and charges. It would be helpful to remember that nonsense term, right? Par V and then series Q. And so this means for capacitors in parallel, the voltage is the same. So like these two here, the 6 and 12 microfarad capacitors, those values aren't the same, but the voltage has to be the same. The charge, not so much, right? So if you can imagine the charge moving around this wire here, moving around the circuit, it hits that node, that fork in the road, and it has an option. Those charges have an option to go this way or this way, and then be, I guess, deposited or built up on either of those plates. So between those two capacitors, the charge is shared, not necessarily equally in this case because the values are 6 and 2, but they're split up some amount. The voltage, however, is the same across them both. For capacitors in series, the charge is the same. So for example, this capacitor and this capacitor have to have the same amount of charge, right? Irrespective of their capacitances. The voltage, however, will not be the same necessarily, okay? It should be noted that the voltage across the entire circuit, every other series element or every other circuit element besides the battery have to add up to the battery's voltage, 9 volts. So let's see what's going on the charge level. Out of the battery, the negative terminal, right, that effectively repels negative charges, well, away from it, over here. And so the negative charges build up on the bottom plate over there. So we can draw it like that. Bottom plate becomes excessively negatively charged. That kind of polarizes this middle segment and makes the top plate of that capacitor positively charged. By the way, we'll call that C4. Okay. So the bottom plate, because it's net negative charge, that in turn repels negative charges in this wire segment here. And if you notice, this segment right here is not touching whatsoever this segment or these segments, right? This right here is completely by itself. So the charges in this segment here remain in that segment. They just are rearranged because there's a net charge on this capacitor. So, getting back to what happens. This bottom plate repels the negative charges in this segment, and they're deposited on these plates here, thus making those plates negatively charged. Okay? The presence of that bottom plate being negative for capacitor 4 attracts all of the positive charges in this segment down here. Okay? So you may get tripped up and think, well, these negative charges, wouldn't they be attracted to the positive charge? Yes, but no, right? This repulsion is stronger in essence, right? So the right plates for now, what I'll call capacitors 2 and 3, 2C3, the right plates are negatively charged. That induces a positive charge on the left plates. Okay? And just like what happened before, that self-polarizes, or induces, if you will, the negative charges to move over here to this top plate, right? The fact that that plate and that plate is a negative charge repels the negative charges in this segment as far away as it can. And so what happens is that they all end up on, well, the top plate of what I'll call C1. Okay? And again, that in turn creates a positive charge on the bottom plate of C1. Okay? Which in turn, just like before, this top plate is negative. That repels the negative charges into the battery. And now, yes, those negative charges are also attracted by this positive plate of the battery. And then they're continued on and moved back on through. Okay? Just like I mentioned before, the charges in this segment are just rearranged, as are the charges in this segment. They're also rearranged. They do not transfer in between the plates. They remain in the actual wires. Okay? So that's why we can treat all four of these as one equivalent capacitor. So finally, let's take a look at part A. Part A, let's break this circuit down now, right? Step by step. So if I were to draw the battery like this, we have C1, and then I'm going to reduce capacitors 2 and 3 down to an equivalent capacitance. They are in parallel, so if you remember, we can just add up their capacitances, right? So that value I'll call C23, okay? And then one more with C4. Okay. Now we have three capacitors in series, which we can redraw like such. Battery. Very simplistically, battery V, and I'll call this capacitance 1, 2, 3, 4. That's the equivalent of all of them. Okay. So let's see, C23. What was that? Well, it was the C2 plus C3, which was 2 plus 6, which was 8 microfarads. Okay, now to find C1, 2, 3, 4, or in other words, the equivalent capacitance for all of them, let's do it like this because you'll see why in a second. They are in series. You add capacitors in series inversely. So the equivalent is actually equal to 1 over the first one, which is C1, plus 1 over C23, plus 1 over C4. And this is 1 over 8 plus 1 over 8 plus 1 over 8, which is 3/8. Flip and multiply gives us an equivalent capacitance of 8/3 microfarads, or about, what is that, 2.66 or something? Okay, so that's the equivalent capacitance for the entire circuit, all four of those, right? They're both in series and in parallel, but we added them together accordingly, so it doesn't matter. It's 8/3 microfarads. So that's part A. Let's do part B on another page. We want the potential and the charge. Okay. So let's see. Let me copy paste. Copy. Nope. There we go. Oh, it didn't do my writings. It's okay. Try this one more time. Whatever. Whatever. All right, we want the potential across each of them. Well, we need to find the charge first, right? Out of that battery, there's a certain amount of charge that will flow across all four of those. Okay, so we need to find that. Whoops. So let's go. Remember, Q equals C times V. That's the capacitance times the voltage. And in this case, we want to find or use the equivalent capacitance. Okay, this is the equivalent capacitance. Basically, we're taking this circuit here. So there's a certain amount of charge that effectively will be, I guess, built up on that equivalent capacitor. So what is that? This is, what was that, 24? No, definitely not. 8/3. Times the voltage, well, that's 9 volts for the battery. So this is 72 over 3 microfarads, well, microfarad volts, which is coulombs, but this is microcoulombs. And that's, in other words, 24 microcoulombs. Okay, so this is the charge that will be deposited on across all four of those capacitors. All right, so now let's see how much charge is deposited on each of those individually. So for C1, right, the first one, Q1, we basically have C1 times the voltage across capacitor 1. Well, that was equal to 8 microfarads times the voltage. What was the voltage? Remember this saying here? Let's see, the voltage from the battery for this capacitor will be 9 volts. No, I'm sorry. Oh, what am I doing? I'm getting ahead of myself. Sorry, we're doing the voltage, part B. All right, we needed to find the total charge in order to find the voltage across everyone. There we go. So V1 equals Q1 over C1. There we go. Rather, that's the Q that we just found. So this is 24 microcoulombs divided by the capacitance for the first one, which is 8 microfarads. The micros cancel out, and we're left with simply 3 volts. There we go. For voltage 2 and 3, we have to be a little careful, right? We don't necessarily, or we can't necessarily do it straightforwardly as the first one. These are in parallel, right? They, as it turns out, will have the same voltage as the one we just did because they're in parallel, and thus these are in series with the capacitor we just did. Okay, so whatever voltage we find is the same for both of them because they're in parallel. So now we have that charge divided by the equivalent capacitance for those two, so C2, 3. The charge is still 24 microcoulombs. And now what was that equivalent? Well, it turns out to, again, be the same as the first one, 8. So it just so happens that this is the same value as the first capacitor. Okay, so this is the voltage across both capacitor 2 and capacitor 3. Okay, it just so happens that it's the same as that one. So now we have the fourth one, V4, Q over the capacitance of 4, 24 microcoulombs, divided by the capacitance, which was 8 again, and it's 3 volts. Now, notice here, 3, 3, 3. That adds up to 9. It's the same voltage as what the battery itself supplies. And that is key. In other words, the voltage has to add up, that one, plus the voltage for this combination, rather, plus the voltage for this one, has to add up to whatever the battery puts out. Okay? So that's good. That checks our intuition, hopefully, right? We'll talk about that current aspect in chapter 26 a little bit more. Right? All right, part C, the charge now. All right, the charge for each one is fairly straightforward. The charge on capacitor 1, remember Q equals CV. Well, we have the capacitance for that one, 8 microfarads, times the voltage that we just found, times 3 volts, gives us 24 microcoulombs. Okay, good. Now, for Q2, same thing. Q2, 3, we need to check. They're in parallel now. Is the charge the same or is it shared? Capacitors in series, the charge is shared. These are in parallel. So the voltage is the same. The charges aren't necessarily the same. So let's see here. The charge, or rather the capacitance for the second one, times the voltage across the second one. And that's the same for 2, 3. So we have, what did I call 2? 2 was the 6 microfarads times the voltage 2, 3, which we found to be 3. And so this gives us 18 microcoulombs on capacitor, or on, yes, capacitor 2. Q3, very similar. Capacitance 3, and now the voltage, just like for 2, is the same. So this is 2, and this is 3. So now 2 times 3 is 6. Whoops. Microcoulombs. Notice that it holds less charge because it has a smaller capacitance than capacitor 2, which can hold up to 18 microcoulombs, 3 times more because it has 3 times higher capacitance. And then finally Q4, that was 8 times the voltage, which was 3, and 24 microcoulombs. All right, so that's how you find the equivalent capacitance, the electric potential, and the charge for capacitors in series and in parallel. Thanks for watching.